In this example, we're going to consider the motion of a ball as it rolls up the ramp, stops at the top momentarily, and then rolls back down. A lot of people say, well, it never really stops. It does, just for the briefest of moments. It has to stop, or it would never be able to go back the other direction from what it came from. So we're going to consider the motion from 0 to 50 and then back to 0 again. While it's on the ramp, the entire time, the acceleration has to point to the left or down the hill. We would label that as negative for the entire motion. So on an acceleration graph, the acceleration for the entire time, all the way up and all the way back down again, would have to be a negative number. Now we can't distinguish here on the acceleration graph at the moment at which this happens. I do know that it would have to be halfway through the whole time, right? It takes just as long to go up as it does to come back down. So whatever time this is, about the halfway point is when it would turn around, okay? But the acceleration stays negative throughout the entire time. The velocity versus time graph I ought to mark this same location, okay, just so we kind of make sure we get things right. The ball at the beginning of the motion is pointed up the hill. That's to the right, so we're going to say that that is positive. On its way back down, so it's going to stop right here, and on its way back down, the velocity at the end would be to the left and negative. So I need to start at a positive number. At the very top, it needs to go to 0. I decided that was about this time right here on the graph, okay? And on the way back down, it has to be negative. It's going to the left or down the hill. And so the negative would be about the same as the positive. And so if I can draw a line here and actually make it match up, it would look something like that. The tendency and the temptation for new students is to think, well, it gets to the bottom of the ramp and it stops, and then because the ball physically turns around, they think that means the velocity graph would also turn around. The problem with this way of thinking is the ball certainly starts down here at the bottom. As it rolls up the hill, it's getting slower, so the velocity slopes downward, and it stops. And on a velocity graph, stop looks like that dot right there. It stops. If the velocity were to then continue in the positive direction, that would say it stops at the top and then continues to the right, which would be up off the top of the ramp and out of the picture. And you've never seen anything do that. If you rolled a ball up a ramp or up a hill of some sort, you would never see the ball go to the top of the hill, stop, and then suddenly continue going on at faster and faster and faster increasing speeds. It always rolls back down the hill, and that looks like this, matching the fact that acceleration is constant here the whole time. This slope of this line has to be constant the whole time. Now the position graph has to start at 0. Okay, the ball starts at 0, has to reach a point of 50 at the same moment. Okay, so this moment right here is the same as this moment here on both of these other two graphs. And then it has to come back down to 0. Takes as long to come back down to 0 as it did to get up to the top at 50. This is a negative acceleration, so I should have a concave down parabola. Should be flat right there, and then curve back down. I'm not very good at drawing parabolas by hand, but that is the basic shape of what you would get.